Today's problem is find median from data stream. This is going to be in the heaps category, so we are officially done with trees. We did a shit ton of trees, and we're done with it forever. Just kidding. We'll probably do more later on. But we're on to heaps, and this is actually the singular heap problem in the Blind 75, or at least the only one categorized that way. We've actually talked about heaps before when we did merge k-sorted lists. That's another problem where you can use heaps, so we've talked about it there. If you want a little refresher on what heaps are, why they're good, which we'll talk about a little bit more today. This one's officially a heap problem, and we'll talk about why it is helpful for the overall solution. Hello, welcome in. Yeah, let's take a look at the prompt and do a little diagramming. It's actually pretty intuitive, I think, once you have the overall solution, or like the overall like direction of the problem, and then we'll throw a heap into it, as well as throw it into a heap. Great, so here's the prompt. The median is the middle value in a sorted list of integers. With one caveat, for lists of even length, there is no true middle value, so the median is just the mean or the average of those two middle values. So if there's an odd number, like this, then the median is 3. And if there's an even number like this, then the median is the average of these two numbers, which is 2.5. Really easy calculation. It's just the halfway point between these two. I guess technically we are supposed to do a little bit of magic to avoid integer overflow, but we'll see. We'll see if we need to bother with it. Python, we definitely don't have to bother with it, but we'll talk about how we can avoid that in a sec. Okay, so yeah, lots of examples here that we already did, and then for these three, the median is 2, that's the middle term. For these two, the median is 1.5, which is the average of 1 and 2. And if there were only one number, then the median is just that number. All right, so our job today is to implement the median finder class. The methods that this class has, median finder initializes the median finder object, so just creates the thing and does anything that it needs to do to set it up. We have the add num function, which takes a num and adds it to whatever we're using to store the numbers we've seen so far. And then we have the find median class method, which returns the median of all the elements we've seen so far. Okay, so pretty straightforward as far as what we're being asked for here. If you're not familiar with what we mean by data stream, this just means that we don't have all the numbers up front. We're going to get some numbers, find the median of what we've seen so far, get some more numbers, find the median of what we've seen so far. So it'll be a continuous process of adding numbers and finding their medians. Okay, and now the example here, we won't go through all the details here. The overall vibe that we're trying to get is that we're going to create a median finder object and then repeatedly call, supposedly at random, add num and find median. The nums themselves will be between negative 100,000 and positive 100,000. Yeah, actually, binary search is one way we can handle that. For today, since we've already covered binary search, we're going to handle it a slightly different way. Which I think it's actually somewhat fun to think about once you've seen, I think, the strategy that we'll use. But find median will only be called after adding at least one integer to the data structure, so we don't have to worry about, like, it's an empty list, what the hell is the median of an empty list? We'll always have at least one number to look at when we're finding the median. Okay, so yes, actually, your comment is a great segue into the ways that we could handle this. So first, we need to do tabular integration by parts. Just kidding. This was from a student I was working with earlier. Again, we're given a bunch of data. Doesn't really matter what order we're given it in, but let's say our data stream, and again, we'll see this like one number at a time, so we won't have all the data up front, is like 6. Oh, I'll have to say 7 now. Like -1, 5, 11, like 23, and then like -7. I don't know. Doesn't really matter. And in fact, you know what? Let's make a couple of these duplicates. Maybe we'll make this like 7 again. Well, maybe 6 again. Great. All right, so we're going to see these one number at a time, right? So the idea is like when we start, we'll have just 6, and then maybe we need to find the median. And then we'll have 6 and 7, and then we'll need to find the median. Maybe we'll have then -1, 6, and 7, and we'll need to find the median. Yeah, so that's exactly what I was going to say. So binary search is, if we decide to store this as basically just a bunch of lists, or one list that grows, we will need to sort it, right? And not only will we need to sort it, the problem is we'll need to sort it every time we add something in, right? Or at the very least, we'll have to find the next place, right? Now, if we handle this as a true list, like a Python list, one of the problems is like, what if our data looks like this? What if it's like 6, 5, 4, 3, 2, 1, 0? Then every time we insert, so assuming again we keep a list, we don't really even need to sort it. We can basically just say, okay, let's assume it's sorted right now. Let's find the right place for the next number. That technically is a sort, which we would call insertion sort. And that means like, if you're going to put something in, just put it in the right place, like find the location for it and then bump everything back. And the problem with this is if we do it that way and the numbers get consecutively smaller, then we have to bump everything back here and then bump everything back here and then bump everything back here, right? And so what ends up happening here is every time we put in a new number, we need to have O of n time complexity basically to shift back the whole list, right? Not desirable for us because surely there's a better way to do it, right? Yeah, not super efficient. The alternative to this would be to use something like a DEQ, a double-ended queue, where we can say, hey, you know what, this is not too bad if we can go from either end. The problem with that being, it's still overall like an O of n time complexity to put something, like to find the middle, right? Because then you got to go through all of this or all of this, you know. So DEQ, not preferable either here. So far it seems like the thing to beat, the complexity to beat, is O of n for each insert, right? And notice like if there's n total things here, that's like n squared, right? If we want to do all of the inserts. So we'd like to beat O of n for a single insert. And it turns out this is actually where heaps shine. When we need to keep adding, like we don't have all the data up front, we need to have like a general sorted nature, but we don't want to keep having to sort the entire thing. Heaps are great for that particular like scenario. And specifically when we're interested in finding the biggest element or the smallest element, heaps are especially good for us. Now, you may think, well, we don't want the biggest or the smallest. We actually want the middle element, right? So what gives? How do we relate that to this? Well, what we can do is we can, instead of storing just one list, we can store two structures. One of them being the bottom half and one of them being the top half. So let's not do this example because it's a little bit boring. Let's take a look at this one. So let's do a couple more of these, but we'll think about like how we could do this with the heap structure. I just put in I just put in 5, we'll put in 6. So if we decided to do this as two separate data structures here, then it's pretty easy to find the median because it's just, there's a more complex relationship than this, but it's effectively just like whatever is in the, whatever is at the end of the first section or the beginning of the beginning of the second section, right? So I'm arbitrarily making the shorter section like the bigger of the two right here. But if we were to split these over and over again, it's pretty easy to like look at this data and immediately be able to find where the median is, right? So in cases where the bottom half is longer than the top half, it's just whatever's at the end of that first section, right? And in cases where they're equal size, it's just the average of like this guy and this guy, right? The end of the first section and the beginning of the second section. Okay, so here's, I think, the, yes, so this method does have a name, or this strategy is something that we call partitioning. And this means we really just need to split it into two sections. And what I really want to particularly point out here is we actually don't care about most of the section, right? Like many of these numbers, we will never use ever again. Like -1 is never going to be the median, unless we have like a million -1s that all show up at a certain point, right? So I guess more to the point, at any particular time, we don't care about 99% of the numbers, right? We only care about the middle one or maybe the middle two. And so this is a great use case for the heap because, again, for the heap, we can get the maximum or the minimum element in O of 1 time. It's immediately available to us, right? And that's exactly what we're trying to do. We're trying to get either the biggest of the smalls or the smallest of the bigs, right? Or both, maybe. Now I've sort of taken a few things for granted, like how do we balance these, right? Like how do we make sure that they always follow certain rules, like the smaller section always being bigger, and we'll talk about how to do that. But at the core, if we can think of a way to like code this up, this is very advantageous for us. The other half of this is, like I mentioned earlier, I wish I hadn't erased it, but we're trying to beat O of n insertion time, right? And turns out heaps are actually great for that as well. The heap insert, which we often call a heap push, has O of log n time complexity, and that's great news for us too. So not only do we get to quickly find the middle without needing to fully sort the list, we also can insert in just O of log n time instead of O of n time. So yeah, finding the median occurs at the same speed here, right? But inserting is significantly faster because we don't need to go through every element in the list. We just need that log n heap complexity. All right, now one of the, well, actually, you know what, we'll talk about this in a sec. That's pretty much the whole problem. The whole concept is like keep one data structure that is the smalls, keep one data structure that's the bigs, and let's make those data structures heaps so we can always access the biggest of the smalls and the smallest of the bigs. Sweet. All right. Let me think. So in terms of implementation, we're going to do this in Python. One of the ugly things about Python, at least before Python 3.14, so this is lovely that they've changed this. Python only for a long time had, max heaps, I think. Wait, min heaps? Let me think about this. Only had min heaps, I apologize. And what that means is it was really easy to be able to find the minimum of something using a heap, but to find the maximum, basically the workaround is just every time you put something in, make it the negative of what it was before. So kind of a pain in the butt because like we're going to view this as +1, -5, -6, and like we'll have to do some finagling with when we like put things in or get things out. But in short, these are both heaps. And we love that because that means we can access the biggest of the smalls or the smallest of the bigs really quick. So let's code it up. Can threads be related to this? So the problem with threading for this one is that, again, we don't actually know, or like we don't have all the data up front. So really the thing that we're waiting for is like, what is the next number? And we don't know until we call the next part of the function, right? Or till the next time that function is called. So we could thread, but it's not really helpful to us just this time because like the bottleneck is just somewhere else, right? It's not the fact that we have or that we need parallelism. It's just the process itself is single threaded, so to speak. All right, so what do we need to have? Well, when we initialize this, we're going to want to create these two heaps. And I think we have to import heap queue for this. This is just Python's version of heap, which is also known as a priority queue, or it's an example of a priority queue. So we'll say like yeah, I'm just going to say small equals, and then the way we initialize a heap, funnily enough, is actually just an empty list. So under the hood, actually, in Python, heaps are lists. I won't go too much into this today because I think it just detracts from the usefulness of heaps. But under the hood, there's a bunch of like index magic that makes heaps work, basically. Very interesting stuff, but we're not going to cover it in this particular lesson. So small and large are both just empty lists. Yeah, well, so effectively, I'm going to be pseudocoding for you if you only know C++. So I apologize about that. Um, yeah, you know what? I could probably do this in C++, but the convention for these so far has been Python, so we'll stick with it for tonight. But maybe my challenge for myself will be to do this in C++ later. Wow, the Neil Terrell head pop in is crazy. All right, so we'll have the small list, the large list. I think that's it. We don't need to like initialize them as heaps. We just need to treat them as heaps going forward. Okay, so here's what we'll do is every time we add a number, we're going to figure out, do you belong in the smalls or do you belong in the large? Now, the way we can figure that out, and let me actually pull up the diagram, is by comparing the thing that we're about to add to either the biggest of the smalls or the smallest of the bigs. Now I'm gonna, let me actually give myself some more space here. I'm gonna arbitrarily say, and it doesn't matter, again, we could do this where like the large heap is always longer, like equal to or longer than the small heap. I'm gonna arbitrarily say like, I just want the smaller heap to be the bigger one. I don't know, it doesn't really matter how you do that. So there's two choices, right? Two partitions. Either we add it to the small or we add it to the big. Now, how can we know? Oh, so we can say if the number that we're going to add, don't like this one very much, is less than, you know what, I need to look up real quick. No, wait, actually, I know this. Python definitely uses min heaps. So what that means is it's really easy to get the minimum element, but if we need the maximum element, we have to do some like weirdness. Now specifically though, we want if num is less than heap q. Oh, no, actually, hold on. It's just going to be small 0. So this is the way, like this is the Pythonic way to get the min of the min heap, basically. It's always stored at index 0. Like I mentioned earlier, under the hood, this is all like index magic. So if num is less than small index 0, now here's the problem. For the small heap, the numbers will all be negated. So when we pull them back out, we also need to negate them. It's weird. We're just going to accept that that's how it works. Okay, so what we're trying to say here, and I'll actually leave a comment so this is more explanatory. If num is smaller than the biggest small. And what we mean by this is like if we can find the biggest one here, right? And the number that we're about to insert is smaller than that, then we know it belongs in the small heap, right? Yeah. Now, why are we negating it? Again, this just has to do with how Python is handling these. Since it has to be a min heap, what we're going to say is basically like, oh, instead of calling these -1, 5, and 6, let's call them 1, -5, and -6. This is how they'll be stored in the heap, but the numbers that truly belong there are still -1, +5, and +6. Like this guy is the biggest, quote unquote. In terms of negative numbers, it's the smallest, right? I know it's ugly, it's hideous. I don't know why Python has done this for so long. And now in Python 3.14, you don't have to do this anymore. You can just make it a max heap, but it's a min heap with negative numbers, which is effectively a max heap. I know, hideous, gross, we're going to have to live with it. Okay, so if num is smaller than the biggest small, then we are going to put num into that heap. And here's the syntax for that. We'll do heap q.heap push. Negative num, because again, anytime we insert or remove from this small heap, we're going to negate things. Okay, and then I forgot to say, actually, this is not the right syntax. We need to say which thing we're going to push it to and then push it. So this is the syntax, heap q.heap push. Which heap do you want to put it in, and then what do you want to put in there? Okay, and then I'll say actually if num is less than or equal to, just because something needs to capture the equal to scenario. Well, yeah, it doesn't matter. It doesn't matter. Something needs to, like, we need to pick one. It doesn't matter if you do less than or equal to or less than, as long as you pick an appropriate place for it. So like, for example, in this scenario where there's both 6s here, it's like, well, which one do we put it in? I'm going to arbitrarily pick the smaller one. You could have picked the bigger one. It wouldn't make a difference. So then we have the else. In fact, you know what? I'll do this, and then the else scenario will be if num is greater or equal to the biggest small. So if it's bigger than or equal to the biggest small, then we're going to put it into large. And since large actually is a min heap because we want the minimum value of the larges, we just push num normally here. Yeah, and it is kind of like a map. It's like we know in our heart of hearts, right, that this is really supposed to be -1, 5, and 6, but the data will say the reverse so that we can take advantage of that min heap nature. Okay, so we got that. Okay, now here's the other thing. We need these to retain a certain relationship of size, right? We can't have one being 5 elements and one being 2 elements because then there's no way for us to find the median, right? So now that we've pushed an element, if they got out of whack, like if it's 4 and 2 right now, we need to rebalance them, right? So here's what I'll say is if, let me think about this. If the length of small is greater than the length of large plus 1. So it's okay for it to be 1 off, right? Because in that case, like, this is just the median now. But if it's more than that, like we push a number, now we have 4 here and 2 here, we have to send one of the smalls to the large, right? Specifically, we need to send the biggest small over to the large list, right? Okay, so if this scenario happens, I don't need to comment this. This is fine. So if the length of small is greater than the length of large plus 1, then send the biggest small to the large heap. Okay, and I'm actually realizing there's one thing that we're going to have to do here. We're taking small index 0 right here, but what if there's nothing in small, right? So I'll say if not small, then we'll push to small. So okay, sorry, I'm getting sidetracked here. So what we need to do is send the biggest small to the large heap, and then that'll put them back in balance, right? So the previous scenario is we have no more than 1 extra in small. Ooh, now what if they're equal to each other and then I push one into large? Like if we're at this scenario and then we put in 8. Wait, I'm gonna need to think about this for a sec. Is there a better way to handle this? So maybe there's a better condition here. If the length of small No, actually, okay, wait, wait, wait. Let me think about this. Let me think about this. We could either always make small, like the longer of the two, just so it's easy to find the median, is what I'm thinking. Alternatively, we could just say, well, fuck it, just put it wherever it goes, and then when you find the median, you can figure out which one is longer. I think that might be the better way to do it. So here's what I'll do. I'll say if the difference between the two is greater than 1. So I'll say the absolute value of length small minus length large is greater than 1. Ooh. Ooh, but then I still have to pick. So yeah, you know what? So either way, either way, we need to send one to the other, right? So would it be better for us to just always say like, let's just make sure that small is the longer one? I don't know. This is probably arbitrary. It doesn't matter which one you pick here, really. But yeah. I'm getting so this is literally I'm over engineering this way too much. I should just pick one. I'm just gonna pick one. Okay, so we'll say if the length of small is greater than the length of large plus 1, then we'll do this, the thing I said earlier. I don't know why I deleted it. Send the biggest small to large. Okay, so ooh, there's I could probably like one-linerify this. I don't know if I want to. We want a heap q dot heap push large, and what do we need to send? So this is how we remove and get the biggest small. Heap q dot heap pop small. And then again, since we're removing from that small array, we actually need to negate this again. Okay, and then on the other hand, if the length of small, I'll say it the other way actually, if the length of large is greater than the length of small plus 1, then we need to do the reverse. We need to send the smallest large to small. God, so many words. Okay, but same concept here. We'll heap pop from large and send it over to small. And I'm just gonna put a organizational comment here to say heap lengths of lists different by no more than 1. And again, this is going to be so it's easy to find the median later on, right? Okay, I think that might be it. So if there's nothing in small, we'll add to it. If the thing that we're adding belongs in the small list, because it's smaller than the biggest small, then put it in here. Otherwise, if it's greater than or equal to the biggest small, put it in here. And we're heap pushing to make sure that we're always able to access the smallest big or the biggest small. And then if the lengths of them is more than 1, so we need to be able to like keep them balanced so we can find the medians easily. If the length of small is too large, then send the biggest small over. And if the length of large is too much, then send the smallest large over. This is actually bugging me. I said biggest. I'm going to say the largest small, just for consistency. Okay, and then we're good. We don't have to return anything, so that function should be set to go. And this makes finding the median pretty easy. If the length of I'll say the length of small is greater than the length of large, and we know that they're never going to be off by more than 1, then we will return the biggest small. And again, we negate it just because that's how heaps work, or how max heaps work. On the other hand, if the length of large is greater than the length of small, then we need to return the smallest big. Okay, and then finally, if it's neither scenario, if they have the same length, then we need to return the average of the two, which is negative small 0 plus large 0, and then divide that by 2. Yeah, so the only caveat I have here is that this actually might cause integer overflow in other languages. So another way we could do this is we could return the difference between the two numbers. I hate this. The difference between the two numbers divided by 2. So it would be this plus large 0 minus negative or plus small 0 divided by 2. So this would avoid integer overflow because we're always calculating a difference that has to be valid. We divide that by 2, and since the original numbers were valid, that means that we're going to get another valid number, right? Ugh. Okay, I don't even know if this works. We probably should have tested this as we went, but here we are. Let's find out. I'm just going to run it. Let's see what goes wrong. Oh, this is so sad. This whole time it should have been self.small, self.large. Because that's just how Python works. These are class variables. Okay, let me correct all of these and then we'll test it one more time. Heap push self.large, self.small, self.small, self.large. Jeez, I really did this a lot, huh? Self.small. Me when I'm not in an IDE, so I can't just find and replace. And I'm on an iPad also. And I missed a small right there. God, what a day. What a life. I bet I missed one. Man, I did miss one. Where is it? I missed 2. My base language? You know, I actually only coded in C++ for a long time because that's where I started. And all of my community college stuff was C++. And then I taught myself Python when I transferred. And I taught myself JavaScript when I applied for this thing I did called the Snap Academies. And then I started using TypeScript. So yeah, I've also taken like a class in Java. I don't know, so lots of languages, but I guess I'm a little bit of a polyglot now. Oh man. Why can I not? Okay, let me hit the run button. Oh, this time it just didn't work. What's going on? Oh, now that's not what I was hoping would happen. My guess... Oh, you know what? You know what? Oh, no. These should be mutually exclusive. Okay, so the first one worked and then it stopped working, which is great. I think overall the approach was correct. I just am thinking about where to start debugging this. Well, okay, actually, let's think about this. We returned 1, which was right. And then we added the number 2. Oh, I have this in reverse. I was like, isn't that right? Okay, so we returned 1 and then 1 again. What is the reason for this? 1 was correct, and then we added in 2. Now, where would that have gone? It would have gone here, which is kind of what we wanted, actually. Oh. Hold on. Nope, I know what happened. We pushed into... Okay, well, let me actually say what happened. So we had 1. Since there's no small list right now, we put it in there, right? Okay, the next time around, we're putting in 2. Well, there is a small list now. The number is not smaller than that, so it goes into large. Wait, hold on. If not self.small, self.small.append negative num. You know what? That's not what I thought was going to happen here. My hunch was that we had pushed into large first, but that can't happen because we have this little guard clause. Here's what we'll do just to be able to diagnose this quickly. I'm going to put a print statement right here that just prints self.small index 0 and then self.large index 0. Oh. So here's what's interesting. We're getting 1 and 1 and then 1 and 1 again, huh? So there's something wrong happening with how we like push from one to the other. Okay, so this is definitely not happening twice right here. And right here, we're removing. Huh. It seems like this is being triggered twice, and I have no idea why. Because we add in a 1, and then we add in a 2, and then we add in a 3. So at no point should we have 2 1s, right? Somehow the 1 is being duplicated, and I'm not really sure why. Let me take a look here. You know what? Actually, I think it is this right here. I'm going to put this, I think this is throwing off the, so here's what I'm thinking, is that we put that 1 in kind of arbitrarily. Ooh. No, I'm not sure where this is going wrong. Okay, I'm going to stop yapping for just a sec and try and follow the logic a little bit better. This... Oh. I'm a dummy. If this happens, we're done. That's the problem. We were putting in the 1 right here, and then we were going, oh, hey, there's another 1. Like we were continuing, right? We needed to stop right here because we put in the number to where it belongs, right? Okay, hopefully that solves our problem. Oh, thank God. Yeah, so that was the only problem, was we needed a return right here because we've actually found the correct place, right? Otherwise, so if assuming that there actually is something in that small list, now we can start doing comparisons about the heaps, right? Okay, let's see if this works in general. Great. Okay, so that was our only problem. We just missed that 1 return statement because, And I wish there was a nicer way to do this, like they would give us the first number immediately, because it's a pain. I hate from an elegance perspective that we have to check this every time, even though only the first number um, cares about it. Oh well, not a huge deal. But yeah, that's that. And yeah, it's very well commented here. We did a little debugging. This session had a little bit of everything. So thanks for tuning in. Any questions I can answer for you while I've got you here? Sweet. Great. Yeah, I guess we talked about time complexity and everything already, so we'll call it there, and we'll be back for another one tomorrow. What's the topic? I don't even remember. Tomorrow is backtracking. I low-key hate backtracking, but it's fine. We'll talk about it. All right. Well, have a good night, and maybe I'll see you tomorrow.